Joseph sir, good morning.
Sir. Morning, sir. Satya, sir.
Hi.
Rajaji joined?
Yeah.
Sir joined.
I am already here.
Oh, sir. Good morning, sir.
Good morning, Joseph.
Adarsh, we can start.
Himanshu, now over to you.
Yeah. Hello, am I audible?
Yes, you are.
Okay, so good morning, everyone. On the day 2 of the QuantumFyed talk, today's topic will be the story of neutrino and iono. The talk will be given by Professor G. Rajasekaran, and to introduce the speaker, I would like to hand it over to Professor Joseph Prabhakar. Over to you, Professor.
Am I audible to everyone?
Yes.
Yes.
Very good morning to all of you present here. So it's my highly privilege to introduce Professor G. Rajasekaran, whom I have known last almost 12 years. So G. Rajasekaran, fondly called Rajaji, had a simple beginnings from Kamudi, remote area from Ramanathapuram district of Tamil Nadu. An alumnus of American College and Madras Christian College, obtained his PhD from University of Chicago in the year 1964. He has been associated with the Tata Institute of Fundamental Research, TFR, and also he was a professor and head of the Department of Theoretical Physics, University of Madras, and the Institute of Mathematical Sciences, joint director and distinguished professor. Currently, he is professor of emeritus at the Institute of Mathematical Science and adjunct professor at the Chennai Mathematical Institute. In the career spanning around 6 decades, Professor Rajasekaran published more than 180 research papers and made fundamental contributions in high energy physics. He is still active in teaching physics and an important member in the INO project. He is the fellow of Indian Academy of Sciences, Indian National Science Academy, and National Science Academy of India. He is the recipient of Magnath Saha Award, FCCI Award, S.N. Bose Medal, as well as Homi Baba Medal as a topper of first page of Bark Training School. So this is a kind of introduction, but I would like to add furthermore. So I know Professor Rajaji for the past 12 years as a student. I learned quantum mechanics from him in his Sunday class. In fact, other than this, whatever I read, he is also excellent science writer. So I should really say to this audience, not only is writing popular science article in English, he's also write popular science article, physics article, high energy physics article about INO in Tamil in his own mother tongue. So in fact, every month he used to write a lot of articles. This must be a very, very important lesson to all of us. Such a age, almost around age of 85 or 84, every month he is writing some articles in Tamil. It's a very, very, not only English and also, so every week, every month we can see his article in Tamil and English. So it must be, it implies that, so everyone who are in the science field should not only, of course, we are learning science in the English language, at the same time, we should take the science to our people. So the best way to communicate this, we should express the science in our own mother tongue. So this is the best example, best lesson that I learned from him. And of course, everyone must learn from him. And I want to mention, we heard about Sir C.V. Raman, we heard about Meghnad Saha, we heard about Chandrasekhar. So Professor G. Rajasekaran, I think as far as I know, the person who attended Sir C.V. Raman lectures. When Sir C.V. Raman was alive, when he was in Chennai, Professor G. Raj, when he was taking classes to us, he used to say the story. So as a student in the year 1950 or 51, so every month, monthly once, I think, Sir C.V. Raman used to give lectures in President's College, Chennai, where he studied and he worked. So in fact, really, it is very, very highly, really very, very nice to see that such a person who is associated, who is attended Sir C.V. Raman lecture, and also he is a student of Subramanian Chandrasekhar. So as I read in his by a small detail, he done his MSc in Chicago University, where Chandrasekhar taught him general theory of relativity, mathematical physics. So he also fondly, closely associated with Chandrasekhar. I think, as far as I know, he also known he could have met Saha. So in fact, I can say that after the first generation of physicists in India will be Chandrasekhar or Sir C.V. Raman or Saha. The second generation, on par with, I can compare on par with Saha and on par with Raman and Chandrasekhar. I can see Rajasekaran as a second generation of physicists in India. In fact, in this juncture, I really happy to see, and we are very happy to listen his talk. Today, he is going to talk about the neutrinos and the India-based Neutrino Observatory. In fact, the neutrino INO is his brainchild, his dream. I hope the INO must come into full effect, full operative very, very soon. We are very fortunate to his lectures from his own mouth about his own dream, own child. Over to sir.
Hello. Can I start?
Yes, sir, you can start.
Professor Rajasekaran, sir.
Yeah.
Yes, sir, please.
Can I talk? Can I start?
Yes, sir. So please, sir.
First of all, let me thank the organizers of the Quantum Club to give me this opportunity. As many of you might know, I gave one talk on the standard model Higgs boson and what lies beyond last Sunday. Now this is my second talk. I give my thanks to the organizers for giving me this opportunity. I would like to thank Joseph Prabhakar for the very kind words he spoke about me, introducing me. In fact, he said things which go beyond the reality. But nevertheless, I would like to thank him. So let me start talking about the topic, neutrinos and the India-based Neutrino Observatory. Next, please. Very important discoveries have been made in the past 20 years in neutrino physics and neutrino astronomy. Neutrinos are elementary particles which fill the universe in great abundance but are very elusive. They hardly interact, so it's very difficult to study them, and they don't affect us at all. In fact, trillions of neutrinos, 10 power 12 neutrinos, are passing through our bodies every second without affecting us. Our sun alone is producing plenty of neutrinos through the thermonuclear fusion reactions, which are giving us heat and light and keeping us alive. 70 billion neutrinos per centimeter squared per second at the Earth. Those are the number of neutrinos produced by the sun. I will soon show you how to calculate this. It's very easy to get this number. Next, please. One of the most important developments in the last decade, last 1.5 decades, is the direct experimental proof that the sun's heat and light are produced by the thermonuclear reactions in the sun. The second important discovery is that neutrinos have mass. Until this discovery, it was thought that neutrinos are massless particles like photons, the quanta of light. This discovery is expected to have a profound impact on our knowledge of the universe. Next, please. Of all the elementary particles of nature, neutrinos are the most elusive, the least interacting particles. Studying the properties of neutrinos is a crucial step in our inward bound path of discovery, unraveling the mysteries of matter and the forces that hold it together. The resulting understanding will explain not only what we see around us today, but also can be taken back in time and apply to the very early universe. How did the universe begin? How did it evolve into its present form? This is the importance of neutrino research. Next, please. The universe is supposed to have started in a big explosion, which is called the Big Bang. And in that explosion, presumably equal amount of matter and antimatter would have been produced. Now we don't see any antimatter. Antimatter is to produce it in the laboratory to study it. So what happened to all the antimatter? How did it disappear? The present day universe contains only matter, no antimatter. This is one of the important questions in cosmology, and neutrino research will help to solve this problem. I will say it briefly here. Later, if there is time, I will come back to this. If neutrinos are Majorana particles, then this disappearance of antimatter can be explained. And that is the fundamental importance of neutrino research for understanding the cosmos. So as far as the importance is concerned, neutrinos are as important as the cosmos. That is what I'm trying to show in this balance. Next, please. These developments have led to very active planning of many more neutrino laboratories all over the world. For a considerable part of neutrino physics is yet to be discovered. What has been discovered only is like the tip of an iceberg. So a grand competition is going on in the world. United States of America, Canada, Europe, Japan, Korea, China, in all these countries, big neutrino laboratories are already functioning and more are being planned. What about India? Next, please. India was a pioneer in neutrino physics. The very first detection of cosmically produced neutrinos was made in the Kolar Goldfield experiment in 1965. But the KGF laboratory was closed in the 90s because of the closure of the KGF mines. The owners of the KGF mines decided to close it because there was not enough gold. But this was a mistake. Scientists should not have allowed this laboratory to be closed because scientific truth is more precious than gold. But anyway, there's no point in crying over spilt milk. It's gone. It is the study of this cosmically produced neutrinos that led the Japanese physicists to win the Nobel Prize twice, once in 2002 and again in 2015. We missed the boat. Can we recover the lost initiative? We can and we must. The India-based Neutrino Observatory project has been conceived with this objective. Next, please. So this is the plan of my talk. Introduction, that is over. Then I will give a brief summary of our present knowledge of fundamental physics. Then I will go through the brief history of neutrino physics. In fact, I would like to stress that the best way of learning any topic in physics is to learn it through the history, how each of the things was discovered. So from that point of view, solar neutrino physics is very important. So I will spend more time on it because of its historical importance. Then I will include atmospheric, I will come to atmospheric neutrino oscillations, and then the whole story of oscillations I will describe, and how the neutrino mass was discovered through the oscillation. That's what I will talk about. And then I hope there will be enough time. I will go to the INO. Next, please. I now give a capsule presentation of our current knowledge of fundamental physics. 100 years of fundamental physics, starting with the discoveries such as radioactivity, electron, neutron, and positron, and revolutionized by relativity and quantum theory, have culminated in the summary I am going to give. According to this knowledge, the universe consists of two components, particles and fields. Next, please. The particle sector consists of the quarks U and D, the proton and neutron, which are the constituents of our nuclei, are really made up of three quarks, either U or D. And then if you add the electron, so these three particles are the constituents of whatever we see in the universe. Then if you add nu E, thermonuclear fusion reactions also are understood because in every thermonuclear fusion reaction, neutrino also has to be emitted. So this is called the electronic doublet. This is called the quark doublet. About all these things I talked last Sunday, so I will be very brief. So this quartet of particles is sufficient to build the whole universe. However, for an important reason, nature has decided to repeat it twice more. In addition to the garden variety electron of which all of us are made, there is a heavy electron called muon, which actually was discovered by Homi Bhabha. And then there is still heavier electron type of object, charged object, like tau, it's called tau. And with each of them is associated a neutrino. So these are called different flavors: E flavor, mu flavor, tau flavor. So there is a mu E, mu mu, mu tau. These are the three important neutrinos which are the main subject of my talk today. Like that, the quarks also are repeated twice more. One doublet, here another doublet. All these particles are as important as these particles. We don't see them now because they all have decayed, because they are heavier. They are all decayed, leaving the universe to be made up of only these particles and the neutrinos. Now, next comes to the field sector. These objects are subject to three kinds of forces: electromagnetic force, of which all of you know, weak force, and strong force. The electromagnetic force and its quantum is called photon, gamma, and the weak force, there are three quanta, W plus, W minus, and Z, and strong force is mediated by 8 quanta called gluons, and the gravitational force is mediated by a quantum called graviton, but we will not say much about this. Actually, we don't have a complete theory of quantum gravity even now. That was the topic of last Sunday's talk. Next, please. So the history of neutrino physics is summarized here. Neutrinos were born in the mind of Wolfgang Pauli, the same Pauli whose exclusion principle all of you know about, in the year 1930. See, those days when beta decay was discovered and the beta particles, which are nothing but electrons, were studied, their energy distribution, a funny thing was discovered. Whereas the alpha particles and gamma particles coming from nuclear decay had unique energy, the energy being the difference in the energy levels of the final and initial state of the nucleus. The neutrinos which were coming out did not have a unique energy. It was a continuous distribution of energy going up to a certain maximum energy. Now, how to explain this? Famous physicists like Bohr even were prepared to give up energy conservation. They said maybe energy conservation comes only in macrophysics. In microphysics, maybe energy conservation is not there. Such drastic solutions were offered. But Pauli, what he said was, maybe along with the electron, an unseen particle also is emitted, and that takes away part of the energy. That is why electron does not come out with unique energy. Now, I don't know how seriously Pauli himself took this his own idea, because he did not even publish this idea. He just wrote it as a single para in a note to a conference which he did not attend. The person who took this idea seriously was Enrico Fermi. He built a complete theory of weak interactions based on the emission of neutrino, and by using the quantum field theory, which had just been constructed by Dirac 5 years earlier, 1927, was the birth of quantum field theory, and Yukawa constructed his pi-meson theory on that basis, and Fermi constructed the weak interaction theory, in which quantum field theory he used. Electron and neutrino had to be created. Only quantum field theory is capable of doing that, as I explained in the last lecture, Sunday lecture. So that is Fermi's theory of weak interaction, which has stood the ground for almost 40 years until it was replaced by the standard model, which I described last time. In the subsequent 20 years or so, Fermi's theory was subjected to many experimental checks, and in all of them, Fermi's theory came successful. So it was fairly clear, it was completely clear to almost all the theoretical physicists that neutrino existed, because Fermi's theory depended on the existence of neutrino. But there were two experimental physicists, Cowan and Reines. They said, no, that is not enough. If neutrino is there, I should be able to detect it. So remember, this was the year 1954, about 10 years after 1945, when the bombs were dropped in Japan. The nuclear bomb tests were going on all over the world by America, Russia, and so on. And sorry, sir, just Sorry for the interruption. So there's every nuclear fission also produces neutrinos because the fission fragments are beta radioactive. Actually, they produce antineutrinos. So Cohen and Reines said we will go near a nuclear bomb explosion and then detect those antineutrinos. For obvious reasons, they were prevented from doing so, but they did not give up. They went near nuclear fission reactor because nuclear fission reactors were already going on, and they chose the Savarna River reactor in USA and went and detected the antineutrino coming from that. There is a small story connected with that. It seems Pauli had sent a telegram to the committee which was going to give financial support to Cohen-Reines experiment. He sent a telegram saying that don't support this experiment because nobody can detect my particle, my neutrino. But even before Pauli's telegram reached the committee had decided to support Cohen-Reines, and Cohen-Reines went ahead and did the experiment and detected the antineutrino. How did they do it? They had a huge detector made up of some hydrogenous material, some paraffin material, which contains protons, and the protons absorb the antineutrino coming from the nuclear reactor. So antineutrino plus proton gives positron and neutron, and they managed to detect both. How to detect positron? I think many of you might know. Positron annihilates with the electron in matter, giving rise to 2 photons of energy 0.51 MeV, and the neutron also gives a signal. It takes a longer time. It travels a little bit and gets absorbed in cadmium in the detector which they had put, and that gives photons. So both the positron and neutron were detected by Cohen-Reines. So although it was a very difficult experiment, only a few events they could collect. Nevertheless, it was completely believable. So they were the discoverers of the neutrino, or rather antineutrino first. And Reines got Nobel Prize for this some 20-25 years later. Cohen by that time had died. So next, let me go to the KGF experiment, which I already mentioned. Homi Bhabha, when he started cosmic ray research experiment here in this country, he wanted to study the cosmic rays as a function of the height and depth. So he set up a lab. He sent a group to Kashmir. In Gulmarg, they set up a laboratory to study the cosmic rays at a great height. In fact, I visited that Gulmarg lab long ago, but finally after the Kashmiri insurgents came, they had to close the lab. Now it does not exist. Similarly, he sent another group to the Kolar goldfield mine, because Kolar goldfields are one of the deepest mines in the world, 2 kilometers or more depth. And he sent a group to study the cosmic rays, namely the cosmic ray muons, cosmic ray produced with muons, to study them as a function of the depth under the rock, the earth rock. And they set up experiments and studied it. They studied the flux of the muons as a function of the depth down to great heights, and they went down and down. And at some certain depth, the detector did not detect any particle. They made sure that the detector was functioning, nevertheless it did not detect. And they realized that they have reached a depth at which almost all the cosmic ray muons get filtered out by the overlying 2 kilometers of rock, and now their detector is capable of detecting the rarely interacting neutrinos. And they went ahead and discovered them. And that was the discovery of the cosmic ray produced neutrinos in India. Now let me talk a little bit about solar neutrinos. I will talk in more detail here. Actually, it's a summary of whatever I am going to say today. So briefly, Bethe had proposed the series of experiments, which are the thermonuclear fusion reactions, which give us the heat and light on which we are living. And everybody believed it to such an extent that even Nobel Prize was given to Bethe already for this important discovery, important contribution. Again, Davis said that that is not quite sufficient. If sun produces neutrinos, I should be able to detect those neutrinos also. He started the experiment, I think roughly in 1967 he started, and I'm going to talk a little bit more about it later. Briefly, they managed to detect the solar neutrinos. They were the first to detect the solar neutrinos, namely neutrinos coming from the sun. However, they did not detect the number of neutrinos which are supposed to come from the sun. It was only about 1/3. What happened to the rest? Theorists already had an explanation for this. 2/3 of the neutrinos oscillate away to another variety. That's what they said. But nothing was provable because the number of neutrinos coming from the sun was calculated by using the so-called standard solar model, which is the theory of the sun. But how reliable that is? Suppose that is wrong, then they have detected all the neutrinos. So it was not at all clear. And so then the atmospheric neutrinos, which were originally discovered in India, they were picked up and for further study in Japan, and the Kamioka experiment in Japan, or later the bigger Super Kamioka experiment, they showed that the atmospheric neutrinos also oscillate, just as the solar neutrinos were supposed to oscillate. Solar neutrino oscillation could not be established, but here they could establish it because their result did not depend on the absolute flux of the atmospheric neutrinos. A certain ratio, namely the E type, the mu type of neutrino divided by the E type of neutrino, their flux ratio, that ratio does not depend on the absolute number of neutrinos coming from cosmic rays, so it was more dependable. So the discovery of neutrino mass through oscillation, it is the Japanese Super Kamioka experiment which won. But coming back to solar neutrinos, the solar neutrino problem also was solved by a very beautiful experiment which I will describe in detail later in the Sudbury Neutrino Observatory in Canada. So that is the story of neutrino oscillations, how it was confirmed both in solar neutrinos and atmospheric neutrinos study. Atmospheric neutrinos are nothing but the cosmic ray produced neutrinos. Since they are produced in the atmosphere, they are called atmospheric neutrinos. So both the solar neutrino problem and atmospheric neutrino anomaly was solved in terms of neutrino oscillations. Neutrino oscillations can exist only if there are neutrino masses, as I will explain later. The next important discovery which one can refer to is the geoneutrinos, which were detected by another Japanese laboratory called Camland. What are geoneutrinos? Geoneutrinos are neutrinos produced by radioactive materials like uranium, thorium, or radioactive potassium buried in the deep bowels of the earth. They detected them by detecting them and studying their energy and angle distribution. You can know exactly where they are, and hence for the first time you know where the radioactive materials are inside the earth. Not only that, this is the first detection of any chemical in the deep, from the deep earth, and this will help in understanding geochronology. So in geochronology, a new window was opened by the discovery of geoneutrinos by Camland, and later more detailed results were obtained by another laboratory called Borexino in Europe. So next great discovery hopefully will come from INU, so I put a question mark. Next, please. So I first talk about solar neutrinos in detail because of its historical importance. How does the sun continue to produce energy? What is the physical mechanism? That was a great question around 1850 or so, 19th century. And Helmholtz and Kelvin, who two famous physicists, wanted to solve that problem. They said the answer is that see, what is sun or star? It's just a gigantic mass of hydrogen gas, and since it is very big, the gravitational attraction of that pushes them towards the center, pulls them towards the center. So the hydrogen rushes towards the center, increasing its velocity and hence the temperature. So that is how the sun shines. That was their theory. But they, being very good physicists, they also could show that this process can keep the sun alive for at most maybe a million years or 10 million years. But by that time it was known that Earth itself has lifetime much more than that, billions of years. because geology, geophysics had already shown by studying rocks that the Earth's lifetime is of the order of billion years. But how, and also Darwin, who had proposed this theory of evolution, knew that evolution requires a billion years, not just 10 million years or so. So there was a big controversy going on. They blamed each other and saying that you don't know any physics and so on, but they could not conclusively prove anything until new things were discovered in physics. And those new things were the nuclear physics, the discovery of the nucleus by Rutherford in 1911. Once nucleus and the tremendous amount of energy locked up inside the nucleus was discovered, the famous astronomer Eddington suggested that it's the thermonuclear fusion reactions inside of the sun which power the sun. So Eddington will solve the problem. However, it took another 20 years or so for nuclear physics to progress to a level where the master nuclear physicist Hans Bethe in 1939 completely solved the problem. Although Weizsäcker had given a partial solution earlier. Now, Bethe's paper is in physical reviewing. I will give the reference to that at the end, towards the end. Anybody, I think students should read that Bethe's paper. That gives you everything about, everything you want to know about solar physics. Nevertheless, if you look at Bethe's paper, nowhere does he mention neutrinos. It does not include the neutrinos as being emitted in the various processes, thermonuclear fusion process which he is studying. Actually, he is using Fermi's theory. Fermi's theory has neutrinos, but it still does not mention neutrinos. One reason may be, I am only guessing, one reason may be that Bethe thought that if he mentions neutrinos, his paper will not be accepted by physical review. Because those days, neutrinos were not known. Even Fermi could not publish his paper in Nature. Nature rejected his paper that saying it's too speculative, what is this neutrino and so on. And he had to publish it in an Italian journal and also in his German journal. So that is the level of understanding at that time. Anyway, whatever it is, Bethe's stature was so high that in the next 2 decades, neutrinos were completely ignored by astronomers and astrophysicists. If you look at books or papers published by astronomers and astrophysicists, they don't mention neutrinos at all. This is very unfortunate because because observation of neutrinos from the sun is the only experimental evidence for the thermonuclear hypothesis. Otherwise, it is only a theory. Further, neutrinos provide us with a sensitive thermometer to measure the temperature deep inside the core of the sun. There is no other way of measuring it. Next, please. What is the thermonuclear fusion reaction? 4 protons are nothing but hydrogen nuclei. 4 protons combine to form a nucleus of helium-4 plus 2 positrons and 2 neutrinos, and releasing the 26.7 MeV, which is mostly the binding energy of the helium, subtracting the two masses of the two positrons, 26.7 MeV. So it's very easy to calculate the number of neutrinos emitted by the sun. If you go out and stand in the sun, for every 26.7 MeV falling on your head, 2 neutrinos have to be falling on your head. It is as simple as that. So that is what I have given. Total number of neutrinos emitted per second by the sun is the solar luminosity divided by this 26.7 MeV converted into ergs, multiplied by 2 because there are 2 neutrinos emitted. That is the total number of neutrinos emitted by the sun per second. If you divide by 4 pi r squared, r being the distance between the sun and air, you get the flux of neutrinos at the air. And you put in the numbers 7 into 10 power 10 per centimeter squared per second. Namely 70 billion neutrinos are falling per second, per centimeter squared are falling over our body, both day and night, because neutrinos simply travel through the air. It doesn't see the earth at all. A million earths it can pass very easily. So both day and night we are being bathed by this number of solar neutrinos. And there are other sources of neutrinos also in the universe. Okay. Although I have said 4 protons combined, the probability for 4 protons to meet at a point, namely within 10 power minus 13 centimeter, which is the diameter of the proton, is almost 0, even in the deep core of the sun where the densities are very high. What happens is a series of reactions which are equivalent to this. That's what I describe in my next slide. Next slide, please. So what happens is the famous carbon cycle, which is I think given even in high school textbooks, +2 textbooks. So a carbon-12 nucleus absorbs a proton, becomes nitrogen, and nitrogen absorbs a proton, becomes oxygen, and so on. And finally carbon-12 comes back. So carbon-12 itself is not consumed. It only plays a catalytic role. And neutrinos are emitted, the energy is emitted. And if you add and subtract all the particles coming from the left and the right of the series of reactions, it will amount to that reaction which I mentioned earlier. I want to say one thing more. Can you go back to the earlier transparency, please? This is actually the most I wanted to mention, emphasize that this is the most important nuclear reaction for life, because our whole life depends on this. Next, please. So that is the carbon cycle. But the carbon cycle itself is not the main source of energy production in the sun, because there is very little carbon in the sun. It is in the older stars, carbon, there is enough carbon, that will be the main thing. And the main source of thermonuclear fusion reaction is the so-called PP chain in the sun, is the PP chain. Namely, proton absorbs, proton combines with another proton to make deuteron, deuteron plus positron plus neutrino. And that deuteron absorbs another proton and becomes tritium, triton, and so on. So it's a series of reactions, which again, if you add and subtract all the particles on the left and right of the reactions, it will amount to the same reaction which I showed in the earlier transparency in the rectangle. That is called the PP chain. And PP chain has many side chains. It's a very complicated thing. So one has to calculate this, use this in order to make the calculation for the number of neutrinos produced. The number of neutrinos produced, the overall total number 70 billion, which I mentioned, any high school student can calculate. But that is not enough for physics, because to detect the neutrinos, the detector is generally energy dependent. Most of the detectors detect only neutrinos above a certain energy. So we need the energy distribution of the neutrinos, and that can be done only by solar physics. Solar physics have constructed an elaborate model, again another standard model, standard solar model it is called, and the main result I have summarized here. You find that the dominant branch of the neutrinos in the sun, namely more than 99%, 99.75%, are unfortunately low energy, too low energy to be detected, up to 0.4 MeV only. They are called the PP neutrinos. It comes from the first reaction which I mentioned, namely PP going to deuteron. And there is a very weak branch, 0.01% only, but it goes up to fairly high energy, up to 14 MeV. They are called the boron 8. There is a boron 8 branch in the PP chain which produces that. But it is very weak. Most of the detectors can detect only these high energy neutrinos, namely up to 14 MeV, but then it is very, very weak branch. So this dominant branch is the 70 billion neutrinos which a student can calculate. But in order to calculate this number correctly, you need all of solar physics, because it may be 0.01%, or 0.015, or 0.08%. You cannot calculate it accurately. That is the problem. So hence the role of the standard solar model is very important. Next, please. What is the standard solar model? It is again an evolutionary model. You start with a gigantic hydrogen cloud and allow it to collapse by gravitational interaction, and the temperature in the core goes on increasing, and it reaches a point, a million degrees or above, at which the nuclear reactions are ignited. And you stop after about 4.5 billion years. That is supposed to be the life of the sun. And so that is the model of the sun, which you construct. It is a computer code which constructs for you the standard solar model. Surface temperature, everybody knows, is 6,000 degree K, and the core temperature is 15 million degrees temperature. And the flux of the boron 8 neutrinos, the high energy neutrinos, depends on this core temperature to the power 18. So you see, even a very approximate measurement of the flux of the high energy neutrinos gives you a very good, very accurate determination of the solar core temperature. A typical photon coming from the sun, actually what we see from the sun are only the surface of the sun. Anything which is produced in the deep core hardly comes out, if at all. Again, it takes millions of years to come out, and to come out in a different direction with different energy and so on. Whereas the neutrinos which are produced in the thermonuclear fission reactions come in this, 18 minutes or so, directly without further interaction. And that is the importance of detecting the neutrinos from the sun in order to study the sun properly. So I will now go to the solar neutrino experiment. The Davis experiment, Davis did the experiment with a chlorine detector. He had a gigantic detector which contained, I think, 600 tons of some material, some cleaning material, which contained chlorine and hence the 37 chlorine isotope. The 37 chlorine nucleus absorbs the neutrino from the sun, coming from the sun. Of course, he had put this detector in deep underground in order to get any signal. Otherwise, this detector will be swamped by the other cosmic ray particles. Every neutrino experiment has to be protected by sufficient amount of rock. You go either underground or go inside a mountain. So his detector, the chlorine 37 nucleus absorbs a neutrino. Chlorine becomes argon 37, which is radioactive, and the electron comes out. Now, what Davis did was to detect this argon 37. Argon 37 is radioactive, so every 15 days or so, his detector was purged with helium gas, and because of its chemical affinity, helium gas brought out the argon, radioactive argon atoms. He counted them. So every 15 days, he counted about 5 argon atoms. Just imagine. Actually, Davis got Nobel Prize for this discovery of solar neutrinos, and the Nobel Committee in the citation said that Davis' low-level counting was so sensitive. It is like this: that suppose somebody takes out one grain from the Sahara desert, one grain of sand from the Sahara desert, and then paints it red, and then puts it back into the sand, mixes it. And then you are supposed to detect that single grain of sand from the whole of Sahara desert. And Davis' detection of these argon atoms was like that. That is what the Nobel Committee said. Now, in addition, there were 2 other kinds of experiments I will describe. The chlorine experiment, against the threshold of energy threshold was 7 MeV. So it could detect only neutrinos above 7 MeV. And remember, the PP neutrinos, which are the dominant part, is missed out completely. Only the small boron neutrinos they could detect, only the high energy, only above 7 MeV. Whereas another it is called the radiochemical experiment. Another radiochemical experiment was mounted, actually 2 of them using gallium. And there the gallium was the one which absorbed the neutrino and became germanium. Germanium was radioactive, again it was detected. And the advantage of this was, this had a lower, much lower threshold, and it could detect part of the dominant proton-proton neutrinos also. Remember, I already mentioned in the beginning, but I forgot to repeat it. They detected, Davis detected these neutrinos, but only about 1/3 of what was calculated in the standard solar model. Whereas gallium experiment, since they detected the lower energy dominant part of it, they also detected only a smaller part of the neutrinos which are theoretically calculated. So it's clear that there is a deficiency, no doubt about it. Then there was another experiment, water experiment, which detected the neutrinos by an entirely independent experiment. This was a Kamiko experiment done in Japan. There, the neutrinos coming from the sun elastically scatter the electrons. The electron is pushed forward in the direction in which neutrinos come. So now it is a direct experiment, not a passive experiment like here. It's an active, real-time experiment, because the electrons, by extending the electron direction backward, you will know where the sun was, and the time also was recorded. So this is a real-time active experiment, where these 2 are radiochemical experiments, which have the disadvantage that, see, for instance, I said every 15 days, Davis used to collect the radioactive atoms. but we don't know really whether radioactive atoms were produced by the solar neutrinos. Maybe some other background radioactivity might have produced this. If somebody criticizes that, no, there is no real answer to that. The answer is in here, because here it's a real-time active experiment. So you see the events pointing towards the sun and so on. So definitely it was solar neutrinos. Now this experiment, remember, it's in elastic scattering, and so anyway, I will come back to that later. So these are the three kinds of experiments. What are the results? Next transparency, please. Next. Yeah. From the solar core, the sun produces neutrinos, and we detect them in the earth, just below the surface of the earth. And the ratio, I call it R, the number of observed neutrinos divided by the number of calculated. This should have been calculated. Observed divided by calculated, instead of being 1, it was always less than 1. And the actual numbers are given here. The Davis chlorine experiment about 1/3, and the 2 gallium experiments about half, and the water experiment about half. There are, of course, the numbers don't agree, but the energy thresholds for each of them is different. So even this difference is important information. Now, this itself is a great achievement, because the numbers are not, I mean, less than 1, but it's not like 10⁻⁻² or something like that. It is only still of the order of magnitude 1. But John Burckhardt, who was the leader of the solar physics, he claimed that this discrepancy has to be taken seriously. Why? Because the gallium, sorry, did it go back? I don't know why it got reduced. Okay. First of all, the gallium experiment, for which the standard solar model is not really necessary, even that gave a reduced number. Second, the solar physicists could calculate the details of the helioseismology. What is helioseismology? Just as there are earthquakes, there are quakes in the sun, solar quakes, and the velocity of the seismic waves, and their frequencies could be calculated because it depends on the temperature and density inside of the sun. All that came out right. So they were, reasonably sure that the standard solar model was correct. So the discrepancy between the experimental and theoretical result must be taken seriously. Next, please. Yeah. So something is happening. You cannot blame it on solar model. Something is happening to the neutrinos. What is happening? What is happening is the neutrinos oscillate away and don't get detected. Part of the neutrinos at least get oscillated away. So that is what we should talk about now. Neutrino oscillation. What is neutrino oscillation? Next, please. Go back to what I said earlier, the 3 electronic doublets, electron, muon, and tau. Electron is 0.5 MeV, muon is 200 times heavier, 100 MeV, and tau is 1800 MeV. Now, so here I have pictured the actual reaction by which Davis detected the neutrinos. 37 chlorine interacts with nu E. This is a weak quantum which is responsible for everything, all the weak interactions. So nu E gets converted into electron, and chlorine gets converted into argon. We detect these. But suppose in the process of travel from the solar core to the earth, the nu E gets oscillated away into another variety, namely either nu mu or nu tau. Then nu mu should produce mu minus, but mu minus is 100 times 100 MeV, and nu E does not have enough energy to produce that mass. E equal to mc square. So if nu E gets converted into nu mu or nu tau, it cannot be detected because mu minus or mu tau, mu minus or tau minus cannot be detected in the, cannot be detected because this process does not exist for low energy nu mu or nu tau. That is how nu mu and nu tau get escape from the detection. So Oscillation converts the flavor into nu and mu, and the modified flavor cannot be detected by the Davis detector or galaxy detector. And of course, the Super Kamioka water Cherenkov detector can detect it, because remember, they use the reaction nu plus electron goes to nu plus electron. Only it gives a kick to the electron, otherwise it does not change the flavor. And since nu minus or tau minus are not produced, even nu mu or nu tau will have this elastic scattering. But the efficiency of that process is much weaker, and that is how the Japanese detector also detected only a lower number. That is a matter of detail. I don't want to talk too much about it. So on the whole, the other flavors don't get detected. So that is the story. So let us summarize what we have said. We said that the only way of experimentally proving Eddington-Bethe nuclear thermonuclear fusion hypothesis for the production of energy in the sun is to detect those neutrinos. And these experimenters, the great experimenters, managed to detect them, but they detected only a part of it. And we explain it by saying that part of the neutrinos only they could detect, the other part oscillated away. At this point, I want to mention a short story. Next, please. A famous painter was asked to paint, and he painted what he called cow and grass. But in that painting, there was nothing. It was a blank only. People asked, where is the grass? He said, grass has been eaten away by the cow. And where is the cow? Cow having eaten away the grass has gone away. So it's blank. So our story is like that so far. But in science, we have to prove that if some neutrinos oscillated away, we should be able to detect those oscillated away neutrinos also. And it turns out it is possible. That is what the great experiment in Canada proved. Next, please. What I call the 2-in-1 experiment at Sudbury Neutrino Observatory in Canada. 2002, they achieved this result. What they had was their detector also was like the Kamioka water detector, but instead of water, it was a precious heavy water. Heavy water. Heavy water contains the heavy hydrogen, namely deuterium. Deuterium contains the deuteron nucleus. Deuteron nucleus consists of a proton and a neutron. So nu E converts that neutron into proton. So deuteron disintegrates, but out comes not proton and neutron, but two protons and the electron. This is called a charged current reaction. Anything is mediated by the charged weak quanta like W plus W minus are called the charged current weak interaction. There is another interaction in the standard model which I described yesterday called the neutral current weak interaction mediated by the neutral weak quantum Z. There is no charge exchange, so the deuteron simply gets disintegrated into proton and neutron, and the neutrino remains as neutrino. So whether it is nu E or nu mu or nu tau, this reaction will take place because you are not producing the heavy particle like mu minus or tau minus. So here, if you had put nu mu, you have to produce mu minus and tau minus, which are too heavy to be produced by the low energy neutrino. That is why we explained the solar neutrino deficit. But these, all of them, so this reaction, neutral current reaction, is blind to the flavor. It will work for all. So in one detector, you can detect both processes. Then, if the number of neutrinos as derived from this neutral current reaction is larger than the number of neutrinos derived from the charged current reaction, then you have proved the existence of oscillation. That is what the Canadian experiment did. The number of neutrinos detect flux of neutrinos detected by the charged current reaction, as I have already explained, have to be pi the number of nu E. So I called it pi E, and that number was 1.76, and the number of neutrinos inferred from the neutral current reaction, the flux of the neutrinos from neutral current reaction, pi NC, as I have already explained, is the sum of pi E, pi nu E plus pi nu mu plus pi nu tau, and that number was 3 times this number. So at one go, they proved the existence of oscillations. So roughly 2/3 of the solar neutrinos get oscillated away to the nu mu and nu tau variety. Not only that, and the total number of neutrinos, which is about 5, compared very well with the theoretical result calculated by Bakal et al. Using standard solar model. So not only they proved the existence of oscillations, they proved the Eddington Bethe, the thermonuclear fusion hypothesis. This number also agreed. At one go, the 2-in-1 experiment proved the existence of oscillations and also proved the correctness of the Eddington Bethe theory for production of the energy in the sun. So what is the lesson? See, when, in physics, when we say proof, it is not like a proof in a court. By trying to prove the Eddington Bethe theory, the experimentalists have discovered something new. That is the new thing. What is the new thing? The new thing is neutrinos oscillate. I'm going to describe that. You will see that the discovery of neutrino oscillation is the discovery of the neutrino model. So they made a fundamental discovery in trying to prove the Eddington Bethe hypothesis for solar neutrino, solar energy production. Next, please. But in order to, before coming to oscillation per se, I want to talk a little bit about atmospheric neutrinos. Atmospheric neutrinos, as I already mentioned, are nothing but cosmic ray produced neutrinos. But now we have to shift our attention to GeV, 10⁹ electron volt instead of MeV solar neutrinos, 1,000 times more energies. And so these cosmic ray produced neutrinos, if it is nu E or nu mu also can be detected because nu mu also will have hundreds of GeV terms or even 100 GeV. So it can produce a mu minus. So both will be detected in the detector. In contrast to solar neutrinos, where only the nu E will be detected, in cosmic ray produced neutrinos or atmospheric neutrinos, they can get both nu E and nu mu. Actually, it is the same Super Kamiokka experiment which detected the solar neutrinos, detected the atmospheric neutrinos also. But now they could distinguish the nu E and nu mu. The Cherenkov ring has a different, Cherenkov ring will be sharp for the nu E. Cherenkov ring, the Cherenkov itself, Cherenkov radiation, I forgot to mention how they detected the electron in the water Cherenkov detector. The electron comes out with high energy, with very high speed, and it emits any charged particle which goes with a velocity greater than the speed of light in that medium, which is lower than the speed in vacuum, will produce a shock wave in light, and that is called the Cherenkov light. And it is a Cherenkov light which is a cone, and the circular base of the cone will be detected by the photomultiplier tube. And that circular ring will be sharp for electron and sharp for muon and diffuse for electron. And the Kamiokka people perfected this technique of distinguishing electron and mu. So, so this is a picture of the cosmic ray shower, so-called, on which Homi Bhabha had worked quite a lot. Bhabha-Hitler theory of shower, that is a theory which is used even now to discuss the cosmic ray produced particles. What are cosmic rays? Cosmic rays are very high energy protons which are flying across the universe all over, and very high energy, even 100 GeV or even up, theoretically speaking, it goes to very high energy. But the dominant part is of the order of 10 or 100 GeV. Your high energy proton, of course, it impinges on the upper atmosphere first, and it disintegrates nitrogen or oxygen nucleus and produces many particles. All the energy gets converted into particles, and those particles decay, all of them decay. Many of the particles produced are mesons, pi or k mesons. If you look at this, you will see a pi meson decaying into mu and mu decaying into electron and 2 neutrinos. And if you look carefully, you will see that for every decay, for every 2 electron mu type of neutrino, nu mu, there will be 1 nu e. For every nu mu, there will be 2 nu e. So the ratio of nu mu to nu e has to be 2. So the debris of all these activity is neutrino. That is why we have plenty of neutrinos falling on the surface. Muons also come because they are highly penetrating particles. They penetrate down to 2 kilometers even, as I already mentioned. But if you go further than that, only neutrinos go even to the other side of the Earth. So what is the experimental result for this? Next, please. So the detector is here. This is the detector, and the number of nu mu as compared to the number of nu e in theory is 2, as I already mentioned. The theory is very simple. There is no detailed calculation. That is why this theory is more believable than standard solar model, for which you have to understand all of solar neutrino physics. I mean, all of solar physics. So the theory is 2, and it was verified for the neutrinos coming in this downward direction. Experiment said also 2 for the downward, but neutrinos coming in from all directions get detected here, and this number deviated continuously as a function of the angle, and for the neutrinos coming up from down below the earth, the number became 1. So what is the reason for this? The reason is again oscillations. See, the neutrinos coming from here, for instance, have 13,000 kilometers to travel, and that distance is enough to convert half of the muons to other variety. So that is how the discovery of this was the result of superconductor, for which they were also given Nobel Prize. So they were the first people to establish neutrino oscillations from cosmic neutrino studies. Now we analyze the solar neutrino oscillation, atmospheric neutrino oscillation, and the final result is the solar neutrino discrepancy anomaly is explained by the oscillation of nu e to nu mu, and the atmospheric neutrino discrepancy from 2 is explained by saying that half of the nu mu go to nu tau. So it's a 3 neutrino oscillation, which is somewhat complicated, but it has been done in great detail now. Next, please. I've been talking about neutrino oscillations. What are oscillations? In order to understand oscillations, think of neutrino not as a neutrino, think of neutrino not as a particle, but as a wave. Remember your quantum mechanics. In quantum mechanics, a particle behaves like a wave also. As far as wave is concerned, you can use your knowledge of light wave. Let us take light wave. Light wave, if it travels along the z direction, let us say, it is a polarization in the perpendicular direction, either in the x direction or y direction. There are 2 planes of polarization, either in the xz plane or yz plane. But there is another way of describing the 2 degrees of 2 degrees of polarization of light by using circular polarization. Either it is a circular, right circular or left circular. And you can use superposition principle to get this x polarization, plane polarization is like a simple harmonic motion. This simple harmonic motion can be composed by a linear combination of right and left circular motion. Similarly, right or left circular motion can be constructed by superposing x or y. Both are equivalent ways of describing the light polarization. However, when light travels in an optical medium, then it is circular polarization which should be used in order to describe it, because it is only circular polarization which is well-defined propagation characteristic like refractive index. So you may be producing plane polarized light, but when you send it through optical medium at the beginning of the passage through optical medium, you decompose the plane polarization into its 2 circular components and allow them to propagate, and they will propagate with different refractive index or different velocities. So at the end of propagation, you recompose in order to get plane polarization. You will find it is no longer just pure x, there is a y component also. In other words, the plane polarization is rotated. This is a rotation of plane of polarization in an optical medium. Now come to neutrino waves. In neutrino wave, corresponding to polarization, we have the flavor state. Instead of 2 polarizations, we have 3 flavor states, nu e, nu mu, or nu tau. And again, exactly like here, during propagation, even in vacuum, in contrast to here, even in vacuum, we should not use this flavor state. We should consider linear superpositions of those which are well-defined energies, well-defined mass, and hence well-defined energy. They are called mass eigenstates. They are nu1, nu2, nu3. So they, solar neutrino, in the deep core of the sun, nu e is produced, for instance, and then you decompose them in terms of nu1, nu2, nu3, allow them to propagate down to Earth, and they would have reached the Earth with different phases, And so when you recombine, you will find not only nu e, but nu mu or nu tau also present. So that is the neutrino oscillation or flavor conversion by oscillation. And the probability of this conversion I have given here. Probability of, for simplicity, I don't consider 3, I consider 2, nu e, nu mu, and the mass eigenset nu 1, nu 2. Then the probability of conversion of nu e to nu mu is an oscillatory factor. Sine squared delta m squared is the mass squared difference, m1 squared minus m2 squared, times the length of propagation, namely the distance between the sun and earth, and divided by the overall energy, times a constant factor, which is called the mixing angle. How much of nu 1, nu 2 we have to mix in order to get nu e, that is determined by this angle theta. But in real life, things are more complicated because there are 3 neutrinos. So let us come to the next page, please. Next page. Next page. Yeah. It's a 3 neutrino oscillation. So there are 2 mass square differences, m2 squared minus m1 squared and m3 squared minus m2 squared. And instead of a 2 by 2 matrix mixing nu 1 and nu 2, now nu 1, nu 2, nu 3 mixed by a 3 by 3 matrix. All of you know 3 by 3 matrix has to be described by 3 rotation angles, Eilerian angles, theta 1, 2, theta 2, 3, theta 3, 3, 1. But here it is quantum mechanics. So the matrix is not just an orthogonal matrix, it's a unitary matrix. And so phase is possible, delta. So they are all complex numbers described by delta. This delta phase is very important because since it is complex now, anything coming in complex form leads to matter-antimatter asymmetry. And that is very important for cosmology, as I already mentioned. That is what will explain why the antimatter got removed. So the determination of delta is one of the important things, and that is the understanding of matter-antimatter asymmetry. This is not the full story. This is in vacuum, but in matter, neutrinos do get away. Although the neutrino is not absorbed by matter, matter does affect electron because it is the no, just as photon, of course, glass is transparent to photon, but nevertheless, photon interacts with glass. It is the it is a forward scattering of photon, coherent scattering of photon by the electrons in the medium, which gives rise to refractive index. In the same way, neutrinos also have a refractive index in matter, and that was first correctly calculated by Wolfenstein, and it was applied correctly to neutrino physics by Mikheyev and Smirnov. It is called MSW effect. This is very important because in the context, so because of this, the neutrinos can sense the density profile of matter through which it travels. Next page, please. Here I give you one application of neutrinos. Many people ask what is the use of neutrinos. Neutrinos will be the ultimate tool to study the Earth's interior. Of course, its interior has been studied by seismology, and they have come out with this result. But this is the density. This is the surface, and this is the center of the Earth, 6,000 kilometers. So the density is 0 here, and it shoots up very near actually. Then it slowly varies, but then there is a very large shoot up from about 5 or 6 grams per cc. It goes to more than 10 grams per cc. So that is the core, outer core, and then the inner core. But this is all again a theoretical deduction from seismology. Whether it is really true in every direction in the sun, in the Earth, it has to be studied only by Earth, only by neutrinos. By sending a neutrino beam across the Earth, you will be able to study the Earth's interior in detail and show how the structure, I mean, whether this comes exactly like this, or it has many steps, or whether near the surface, what are the different holes and increase in density, because that will decide where the earthquake will come. So ultimately, this neutrino tomography, the terrestrial tomography by neutrino beams will be used to predict earthquake. But that is all for the distant future. You see, right now we are only studying neutrino physics. Until we have a thorough understanding of neutrino properties, neutrino technology will come. But definitely neutrino technology will come. Everything which is discovered in science ultimately is converted into technology. So neutrino technology will ultimately come, and the prediction of earthquakes will be possible. So it is in this MSW effect is used because neutrinos will sense the density profile. Next, please. Here I have summarized all the present knowledge of neutrinos. Remember, the mass square difference only is determined by the oscillations. And since mass square difference cannot come without mass, that is how it is the discovery of oscillation is the discovery of mass. Can we go back a few transparencies? Yeah, previous. Yeah. So look at this oscillation for in order to have non-vanishing oscillation probability, theta should be non-vanishing and delta m square should be non-vanishing. There has to be a non-vanishing mass square difference. And since we know that there is a non-vanishing probability to explain the solar neutrinos and atmospheric neutrinos, we know that delta m squared is not zero. So discovery of non-vanishing delta m squared is the discovery of the mass. That is I forgot to mention that. Next, please. Next. Yeah, next. Yeah. So these are the result. The mass square difference between 2 and 1 are 7 into 10 power minus 5 electron volt square. See how small it is. And the other mass square difference is 2 into 10 power minus 3 electron volt square, about 30 times larger. Here the actual order is known. M2 is larger than M1. Here we do not know whether M3 is larger than M2 or vice versa. That is why I put small. So the actual order is like this. It may be M1, M2, M3 or M1, M2, M3. Whether M1 is the lightest mass or M3 is the lightest mass, we do not know at the moment. This is one of the questions which INO is supposed to resolve. And what about the mixing angles themselves? They are determined to be 30 degrees, 45 degrees, and 9 degrees. And these are all important phase parameters. This is called CP violating phase. CP is the technical name for particle antiparticle symmetry. If particle antiparticle symmetry is violated, then delta will be non-zero. This has been now known to be non-zero. Some rough determination is possible, but an exact determination is still not possible. So these are the masses. Look how small the mass square differences are, but how small are the masses themselves? This is only mass square differences. Where are they, at what level in the mass diagram it comes? That has to be determined only by the conventional beta decay experiments, by measuring the distribution of electron energy, by looking at the endpoint of the electron energy. You can study whether the neutrino has a mass or not. And the present day experiments give you mu is smaller than 2.2 electron volt. So neutrino mass exists, that is definitely known. But it's so tiny compared to the electron mass, for instance. Electron is the lightest known massive particle, which is 0.51 mm, which is a million times smaller. But the exact number is still not known. The Catherine experiment, which is going on now, might reduce this number and might even determine the actual mass. Next, please. Yeah, this is something, I don't know how much time we have. So I started, can I go on for another 10 minutes or so, 10, 15 minutes, because INO also I should cover.
Yes, sir, you can carry.
Yeah. I already mentioned about these Majorana neutrinos, and so let me say a little bit more. See, if in the periodic table, one nucleus goes into another nucleus, depending on the masses. Only if you go into another nucleus, only if that nucleus is less mass than the original nucleus. But suppose that this nucleus does not have lower mass, higher mass, then many times it happens, we go to another next two numbers, two atomic numbers removed, then it is lower. Then what the nucleus will do is, it will, this is called a double beta decay. Namely, in the normal beta decay, neutron goes into proton, emitting an electron and neutrino. This is the W minus quantum gets exchanged in the beta decay. But here, this itself is not energetically possible. But simultaneously, another neutron in the nucleus also behaves in the same way, becomes a proton, emitting these two particles, then this is called double beta decay. But this is normal beta decay, normal double beta decay, which has been seen and well studied. What is needed now, from fundamental physics point of view, is neutrino-less double beta decay. If neutrino is its own antiparticle, it is called a Majorana particle. If a particle and antiparticle are different, like electron and positron, then it is called a Dirac particle. But neutrino being uncharged, the possibility exists, which was pointed out by Majorana in the beginning. It's called Majorana particle. Then the neutrino, a particle can be the same as antiparticle. And that possibility exists only for the neutrino in the whole of standard model. So if neutrino is its own antiparticle, then two neutrinos themselves can annihilate. Electron and positron annihilate, we know. But if two neutrinos, the neutrino is a Majorana particle, neutrino is the same as antiparticle, then the neutrino can annihilate. So these two neutrinos can annihilate each other and won't come out. I have put it as an exchange of neutrino. Only the two electrons come out. This is called the neutrino-less double beta decay. And this has been searched for in experiments for the last 20, 30 years. It has not been seen. Only some limits have been given. The limits are expressed in terms of the masses again, the linear combination of masses here. And this is again another very important experiment which will be mounted in one of the caverns of the INO laboratory, neutrino-less double beta decay. The feasibility experiments for this are already going on in TA4 and other labs. Okay. So this again an important part of INO. It will be an important part of INO. I think, yeah, now we can go to INO. Next, please. India-based Neutrino Observatory. I call it 16-year saga, but it's actually 20-year saga. We started planning for it in the year 2000. Now it is 2020. That is the level of science we have in this country, in spite of all the hype which is going on about science in this country. For this fundamental experiment, which started 20 years ago, we have still not seen the beginning of it. Next, please. I will come to the reasons at the end. Now, a group of more than 100 scientists and engineers spread over 25 scientific research institutions, IITs, and universities in India is actively involved in the creation of this laboratory, INO. It is a unique basic science collaboration in the country. It was approved for funding by DAE, DSC, and included in the Planning Commission's Mega Science project under the 11th 5-year plan, which is over long ago. In 2015, government approved it and even sanctioned the full money, 1,600 crores for the project. Next, please. What is it? A rock of at least a kilometer thickness is needed, as I already mentioned, to filter all other cosmic ray particles, produced particles, especially the penetrating muon, to enable the detector to detect the elusive neutrinos. Hence, we have to go inside a mountain. We can go into the mine, and that was the Kolar thing, but the Kolar thing is closed. But now, for these big experiments, mountain is more convenient. It's not possible to convey the big equipment into a pit. But in a mountain, you can go by a horizontal tunnel, as I will explain. Such mountains with the right rock quality, namely hardness and stability, are available only in Tamil Nadu. So nature herself has chosen Tamil Nadu for the neutrino project. Next, please. So a huge cavern, 120-meter long, just imagine this length, 25-meter broad and 30-meter height, will be dug under the mountain at about 1.3 kilometers below the rock. And the cavern will be accessed through a horizontal tunnel of about 2 kilometer length. A gigantic magnetized detector of weight 50,000 tons will be constructed inside this cavern and will be used to detect and study the neutrinos. Next, please. The detector will consist of 140 layers of 6 centimeter thick iron plates separated by 2.5 centimeter gaps. The resistive plate chambers, which are the particle detectors, will be inserted in these gaps. So there will be 140 RPS detectors between the iron plates 140 times. The iron will be magnetized to about 1.3 Tesla. Now, why is iron chosen? Because see, these RPC are just 2 meter by 2 meter glass plates, closer all sides, and there will be gas inside. So glass is very important. And for the stability of this whole structure, iron is important. That is one reason. The other, the iron nuclei will become the target for the neutrinos. This experiment is for detecting the atmospheric neutrinos. The atmospheric neutrinos will interact with the iron and produce muons, and the muons will be detected by the RPC. And so the second use of iron is to provide the target. The third is iron can be magnetized. I will tell you why it is magnetized. It will be magnetized to about 1.3 Tesla. The size of the detector is given here. Actually, we can double up because remember the length of the cavern is 150 meters. So it can be doubled up later. The neutrinos and antineutrinos passing through the detector will collide with the iron nuclei and produce muons and antimuons. This will be rare events, about 100 events per year, maybe. It is these muons and antimuons which will be detected by the RPCs. The muons and antimuons will curve in opposite directions in the magnetic field. That is the importance of the magnetic field. And hence, the neutrinos and antineutrino fluxes will be measured separately. This has not been done so far. This is the unique feature of the INO detector and not shared by any other detector or any other planned detector in the world. Next, please. So here a cartoon picture is shown. This is the detector. Here the dimensions are given a little differently from the other until the whole thing is, I mean, these numbers are not frozen. So, so 12 meter height, 16 meter broad, and 48 meter long. And there will be 140 or 150 steel plates sandwiching similar number of RPC gas detector. One unit is shown here, 6 centimeter steel plate, 6 centimeter steel plate, 2.5 centimeter gap. In that there will be RPC. Yeah. Next, please. Considerable excitement was generated by the discovery of the Higgs boson by the Large Hadron Collider at CERN in Geneva in 2012. The INO detector described here will be even, in fact, bigger than any of the detectors in LHC. LHC used the CMS detector and Atlas detector, about 6,000 tons or so, 7,000 tons or so, and this is 50,000 tons. It's much, much bigger. However, having said that, I should also say that the LHC detectors are very, very sophisticated. It's not one detector. All kinds of detectors put up. I hope many of you have seen the picture. It's very, very complex affair. Whereas our INO detector is very simple, basically one type of detector, but in size it is much bigger. So our students can see the gigantic particle detector in action right here in South India and work with it. Actually, this magnet, 50,000 ton electromagnet, will, once it's constructed, will be the biggest electromagnet in the world. Next, please. I think I don't want to talk about it. Next. Although the first priority of the INO project will be to establish those parts of neutrino physics which are still unknown or uncertain, once those are established, attention will certainly shift to mastering neutrino technology, I already mentioned. And some of the exciting applications of neutrino technology, I already mentioned it, so I won't spend time over it. Neutrinos are the most penetrating object, so ultimately the tomography of the Earth will be done by neutrino beams. And geoneutrinos, that will be a new window on geophysics, that also can be done. Next, please. In addition to making major discoveries, INO will benefit generations of students and young scientists and engineers by training them through participation in a major frontline scientific experiment. Student recruitment and training for INO started more than 10 years ago, 15 years ago. In fact, about 40 students have already got their PhDs through work connected with INO, even before INO experiment itself has not started functioning. And they are doing postdoc or doing research in many laboratories all over the world. They are waiting for INO to start functioning, and they will all come back. 40 have already got PhD. The INO project will also include an INO center devoted to R&D in detector technology and student training, which will have far-reaching applications in diverse fields. And that is already functioning in Madurai. Those of you who come to Madurai should go and visit our interinstitutional center for high energy physics. It will be the main nerve center for INO. INO lab, underground lab, the underground, the mountain and the lab which I described are supposed to come in Theni district in Pottipuram area. and that is about 100 kilometer west of Madurai. And in Madurai, we have chosen a site for the main nerve center for INO. And actually there is a prototype of the detector already functioning there, and some people are doing their PhD using that surface detector. Surface detector cannot see the neutrinos because they are sampled by the muon, so they study muon. Muon study also is important in this research. Although the ultimate aim of the project is neutrino physics, it can be easily seen that it is a major engineering project also. Electronics and related engineering and technology will be important, not important part of the project. The signals from the detector will require handling 3 million electronic channels, which I understand is a non-trivial task. The fabrication of the enormous number of sensitive detector elements, RPs, each, as I said, is a 2 meter by 2 meter glass plate, 2 glass plates, sandwiching the gas, and 30,000 of them have to be constructed. So that is also to accurate specification, because I mean the dimensions have to be accurate, and that is a technological challenge. Next, please. So INO will be a unique opportunity for young scientists and engineers, as well as students of science and engineering. More details about this you can see, better see the TFR thing, which is more up to date. So that is the website. You just go into the website, you can get all the details. And more details about the solar neutrinos especially are given in my article in Resonance, which came out 15 years ago, or another article which we wrote in Physics Education. I think that is more or less the end of my talk. But I want to make one important comment. In spite of all I said about INO and the importance of neutrino research, it still has not come up. Why? Because of some people whose objective I will not mention, some politicians and so-called environmental activists. There is one politician who has been saying that I will not allow neutrinos to enter into Tamil Nadu. Even before this champion of Tamilians has uttered this sentence, 10 power 12 neutrinos have passed through his body without his knowledge. But still he goes on saying the same thing. We tell him, but he does not want to listen to us. That is the nature of politicians. Now, we have to fight this superstition. This is nothing but superstition. The students, I have been advising students to join together and get over him. Tell him, don't stand in the way of our progress. You are blocking, INO is blocking our progress. So until that happens, INO will not come. Because INO is not going to benefit me or my colleagues. When INO comes up, I may not be even alive. But INO will be a main laboratory for students, future students, you, as well as even your, because INO as a lab will continue to exist, if not for 50 years, even for 100 years it will exist. So, and that's what we are trying to construct. And these guys are trying to prevent it. So far they have succeeded, but they are not going to succeed forever. We are still fighting over it. One after the other, the obstacles we are removing, it will come up soon. But until and unless you people, students, rise as one body and rise in one voice against these illiterate people, science will not progress in this country. So the role of you people, students, is very important. I want to stress. I will finish with that comment. Thank you very much.
Thank you, sir, for that inspiring message. And now let's open the meeting for questions. So if anyone has some questions or some doubts or wants to add anything, they are free to do so.
So this is Murali.
Yeah.
Thank you, sir, for such a wonderful talk and also your message at the end. You have mentioned about engineers like at the end, because here we are in IIIM, basically engineering institution. how they can take part. So if they want to like take part in this, not only science, you mentioned about there's a scope for the engineers also.
Yes.
How to like if they want to do internship or like some, or take a research in the area, and how they have to approach this.
If you want to join INO, there are avenues open. You can look at that website I had given, and or you can write directly to the INO project director, who is Govinda Majumdar, and say that you want to join. In fact, there are already many engineers connected with INO. All the electronics is being done by engineers, and also the complete design and conception of the detector. There are many components of engineering here. Many BARC engineers are already involved in constructing the INO. They have given they have the complete blueprint for INO. So the electronics is one part, but there are many other parts to engineering.
Thank you, sir. Those who are here can ask sir directly the questions. Like you can unmute yourself and then please ask.
I want to mention one more thing.
Yes.
You know, the data which is coming from these various neutrino events, they have to be stored and disseminated over the 25, although INO laboratory will be in Therni district and there will be the INO center in Madurai, but the work will be done by people distributed over the 25 institutions, universities, research institutions, IITs, and so on. So all that will be handled. Data handling also is very important. And finally, you have to analyze this data in order to get to the physics out of it. So it's a gigantic project. But in the beginning, it is mainly an engineering project. Until and unless the neutrino detector starts operating, the physics come much later. In the beginning, it is completely an engineering project. So the various details of that, I think you can pick up from the website. Website contains all the details, and if more details are needed, I can direct to the relevant persons in the INO project who will help you. So anybody who has any question about either INO or about neutrino physics in general, or about the earlier Sunday article, can also always write to me by email. I will be able to give answer to the best answer possible from my point of view. Yeah.
Yes, sir. Thank you, sir. And sir, you have mentioned about the application, about the earthquake reduction and the can sensitive to the mass density. How far we are away from real application?
So we are far away from that because neutrino physics itself is still in the beginning stage. As I already said, what we know is only the tip of an iceberg. Much more has to be discovered, and neutrino physics has to be perfected before we can apply it. Because otherwise, the application will not give any result. Because we have to know about the characteristics of the neutrino beam completely before we can use it. So the neutrino tomography is the main application which I had mentioned, but I am sure there are many other applications. You see, when Faraday and Maxwell developed the electromagnetism and the electromagnetic waves were discovered, they would not, Maxwell would not have guessed that his electromagnetic wave will be used by you every day. We are using it even in this talk. And we take out a gadget from our pocket and be able to talk to our friends living 1,000 miles away. Or by turning a knob in a lab, the space people are able to control a spacecraft hurtling across billion miles away, a spacecraft. How is all that possible? Through electromagnetic waves. Faraday and Maxwell would not have even guessed about it. So we cannot guess about the actual applications of neutrinos now. We should not think about applications now at all. We should think about only physics, how to understand physics and get all the information about neutrinos. Then, maybe not in our, not in your, even in your generation, maybe in the next generation, it will be applied. There is no doubt that it will be applied. About that, there is no doubt.
Yes, sir. Thank you, sir.
So whenever any pure science is talked about, don't ask for application immediately. You will not get an answer because he will not know. The person who is talking about pure science will not know about all the possible applications. One can only indicate.
Yes, sir.
So you mentioned that the construction of Neutrino
Sorry,
Observatory
I
in
cannot
India.
hear you completely. I don't know. There is some disturbance. Yeah, please repeat.
Hello, sir. Can you hear me now?
Yeah.
Yeah. So you mentioned that there is some disturbance in the construction of Neutrino Observatory in India. So what can we students do to help the construction or the stop the disturbances in the construction of the observatory?
Yeah, you mean this the obstruction
Yes. Yeah.
to the neutrino project. So that's what I mentioned. That actually we are planning to happen soon. I hope because actually the next 5 months or so we cannot do anything because Tamil Nadu State Assembly elections are going on. We do not want to make INO an election issue, and so we are lying low for the moment. But we will be preparing. We are trying to prepare an army of students. Once the elections are over, they will go to all the villages in Theni and Madurai districts and talk to almost everybody. Every week there will be meetings addressed by students. So we are collecting names for that. We are recruiting students. You can all join in that, and so once and then we will tell you exactly what we'll tell you more about INO, about neutrinos, how harmless it is, how all the the fear mongering which is resorted to by these politicians, how they can be effectively answered. All of their fears are completely unfounded scientifically. But since they are all loudmouth, they go on talking about it. See, we are all scientists. So we cannot do that, but nevertheless, we have to do it. Now we have decided we will confront them, not with our talks. We have talked, but we are few in number. But there are so many students. We will create an army of 100 or 200 students who will go from village to village, and that will be the biggest news in Thani and Madurai districts. Nobody can stop you. You see, you are not doing anything wrong. You are only telling the truth. These people are misguiding people. And we are trying to correct that. And once that is there, after that, the way is completely open for the construction. Because money has already been granted. The complete design studies, everything, the blueprints are completely available, everything is available, and it has been stopped by these politicians and the so-called environmental activists. They are saying that environment will be damaged. In what way? This is a deep underground laboratory. Such caverns and tunnels have been constructed in Western Ghats for the last more than 100 years. In fact, Tamil Nadu derives a lot of power from the hydroelectric projects here. Tamil Nadu Electricity Board has been making tunnels of more than 150 miles all over Western Ghats. We are only making a tunnel of 2 kilometers. And how can it damage the environment? Of course, while constructing the tunnel, we have to be careful. Just as the electricity board was careful. Maybe in olden days, they were not careful. But now, since the environmental awareness is there, we have to be careful. But that will be so. We will be careful.
And so, how can a student be volunteer for this endeavor?
Sorry, please repeat. I cannot hear you
I
properly.
mean, how can a student volunteer to spread the words?
Yeah, you have to volunteer. Soon the notices will go from INO to all the colleges in the country, recruiting volunteers who will counter this wrong propaganda. We will definitely do that. We definitely need your help.
Sure, sir.
Meanwhile, try to learn more about INO from the website and try to learn more about neutrinos, because once you join INO, you have to know enough about neutrinos. So study everything about neutrinos, and in general about particles, in general about particle detectors, all that, and about this particular detector, which you can get from the website. Website has quite a bit of information. There are the FAQs, frequently asked questions and their answers. In fact, those also you should study, because that will help you to answer any questions coming from the villagers. So please prepare yourself. All those who are interested in this thing should prepare themselves to be ready, and we will start action in about, as soon as the Tamil Nadu elections are over.
Sure, sir. So, if there are no more questions,
Sure.
yes, sir.
There are some faculty here,
Okay.
so we will ask them to speak.
Sure,
Sir, yes, sir. Sir,
Yes.
here also we would like to learn more from you. Some physics community from Karnool also, some people have joined here, and also there are other faculty here. When college opens, we would like to invite you on the
Oh, definitely. I would be very glad to do that.
Yes, sir.
I would be very glad to do that.
Thank you, sir. Thank you very
I
much.
hope this pandemic will be over by that time.
Yes, sir.
If they come, otherwise I can give you a Zoom talk. I wanted to mention another thing. Anybody who has any question to ask, please ask me over email. I would be glad to supply answers to the best of my knowledge.
Yes, sir. We will share your email address with all the students, sir,
Yeah.
so that they can ask you. Yes, sir. We have a lot to benefit from you. We would like to learn from you, sir. And there are faculty here. I would like to ask them if they want to share their any question or comment about it.
Yes.
Madam Lalita Kumari, madam, if you want to add anything, she's from the college here. She's a professor in college, sir.
Okay.
Or anyone else, please, Sir, Satya, sir, you want to?
Hello.
Hello. Hello, Satya.
Hello. I just I was thinking when your talk was going on,
Yeah.
that in the olden days there used to be a lot of interest in what is called alchemy.
Yes. Yes.
So the neutrino seems to be a key for achieving alchemy. Are there some renewed interest along these directions?
Alchemy was pre-chemistry, right? Where they tried to convert lead into gold and so on.
Yeah.
But it is that kind of research which led to modern chemistry. But now alchemy is there every day. In every laboratory, any nuclear physics reaction converts elements from one to the other. So alchemy is very much true now. Of course, chemists, since they realized that it's not possible, they hypothesize that every element is absolutely stable. I mean, you cannot convert one element to the other. But now we know that is not true. If you go into the nucleus, one nucleus can be converted into another nucleus. So that is an everyday phenomenon in every major high energy physics laboratory, or even in nuclear physics laboratory.
Yeah. After Rutherford, I think
neutrino is a part of nuclear physics. What you say is correct. In neutrino physics, alchemy is taking place. For instance, chlorine was converted into argon by Davis.
Yeah.
So that is alchemy. Every nuclear reaction is an alchemical reaction, although we don't use that word, alchemy.
So the neutrino flavors and then mass eigenstates that you mentioned. This is something like what we know in chemistry, the hybridized states, right?
I see.
Hybridization, sp2 hybridization, sp3 hybridization, where the electron orbitals are taken as a linear combination of.
Oh yeah. I mean, in quantum mechanics, superposition is an everyday affair, right?
Yeah.
So that's what I'm talking about. Nu e, nu mu, nu tau are the states of the neutrino which are produced in the original reaction. But during propagation, you have to go to the mass eigenstates, which are linear superpositions of nu e, nu mu, nu tau. The flavors are superpositions of the mass eigenstates and vice versa. Exactly like the light also there is superposition. So plane polarization can be regarded as superposition of two circular polarizations of opposite direction and vice versa.
Yeah, thank you.
Hello, sir. This is Joseph from our.
Go ahead, Prof.
Of course, thank you for a wonderful talk. But my question is little not related to what you said, little historical one. Actually, during the period, the pre-independence period, Homi Baba and Saga both were there, and in fact, Saga was more famous. But why, instead of Saga, Baba was chosen for nuclear project, the atomic project? Why Jawaharlal Nehru was choosing Baba as a starting point instead of Saga?
See, it is Homi Baba who proposed the nuclear power project. And Saha actually opposed it, as you may know. Saha opposed it. Saha did not believe in solar power. He said, nuclear power. He said we should use solar power instead. And Jawaharlal Nehru agreed with Baba. So that is how the whole of atomic energy empire was built up.
Oh, actually, what I heard that he wants the atomic power to be transparent to everyone. You don't want to keep it as a secret or something like that. So that's the reason that it was not given to Saga like that. I heard, but it's new. What you said is.
What did he say? Transparent.
Transparent means like no, but now like the atomic projects or whatever. Even if you go to IGK or Kalpakam. So those things are really, they keep a lot of security or something like that.
Yeah,
and they don't want to open the whatever the.
I too don't like it. This atomic power project, see, the original aim of the atomic energy department was to make power, but then they got diverted to make atomic bombs. Then security became a big issue. So that is an unfortunate part of nuclear power story in this country. Everywhere it is secrecy, and the Department of Atomic Energy does not share its information with others, which I have also argued against it. They should share all their knowledge with everybody in the country. It's a democratic country. I will tell you a story here. When I was visiting Canada, actually it was in McMaster University in Hamilton, Canada, and I was sitting in the canteen one day talking with other people in the canteen, and through the window I saw a big dome. So I thought it was a telescope, but then they said it's not a telescope, it's a nuclear reactor. The nuclear reactor is sitting by the side of a canteen in the university, because that nuclear reactor is used for research. Actually, I've forgotten his name right now. He got Nobel Prize for using the neutrons for studying solid state. Do you remember the name? It's a very famous name. He got Nobel Prize for it. So that is how atomic energy is regarded in Canada. I do not know very much about America. America also may be very security conscious because it has gone into bombs. Since Canadians don't make bombs, they put the reactor right in the campus. That is what we should have done. We should have completely turned against nuclear bombs. And that is a big mistake which happened in this country, and we are still suffering from it. Because of that, Department of Atomic Energy will forever be suffering. That's my opinion. We are not going to get any benefit from atomic bombs. We are only going to get this security issue, which is a hamper on our freedom.
In fact, sir, what you said is correct. This issue is effect on the INO project also. People are.
That is one reason, because
that's the one reason.
These fellows think that because it is supported by a Department of Atomic Energy, we have something to do with nuclear bombs. They think that this tiny tunnel and cavern will be used ultimately for storing the nuclear wastage, which is completely wrong. See, Department of Atomic Energy, of course, supports it, but Department of Atomic Energy supports mathematics. Department of Atomic Energy supports Tata Institute of Fundamental Research, because because of this Homi Bhabha had two heads. One, he was a promoter of atomic energy department. On the other hand, he was a promoter of fundamental research. Both TAFR, Department of, and Department of Atomic Energy, both were founded by him. But he behaved properly and separating them properly. In fact, since I have been in TFR for 20 years, I know the rules he made for TFR are very different from the rules which he made for BARC, what is called BARC, at that time Atomic Energy Establishment, Trombay. Because Atomic Energy Establishment, Trombay, they were supposed to make power reactor, and so they were mission oriented. In TFR, everybody was given complete freedom to do whatever he or she likes. That is the way he founded this. So, I mean, he did not have any doubt in his mind that India must have both, but he knew how each of them should behave. But the subsequent people have forgotten this distinction. So they are, we are suffering from that. Many of the institutions which are supported by DAE financially think they are parts of Department of Atomic Energy. That is not correct. For instance, IMSC, TAFR, both are autonomous institutions supported financially by DAE. But in time, they have lost their autonomy. Autonomy or freedom has to be used by you, then only it will stand. If you don't use it, they will come and sit on your head. That is what has happened now. They come and sit on our head. I am against this. Actually, it's high time that that we separate fundamental research from atomic energy. A separate agency is created for fundamental research. Now, since INO gets money from DAE, they think that we are going to do this harmful atom bomb research also there. There is nothing to do with that.
Sir, if you are not taking wrong, can I ask one more thing?
Yeah.
So can you share your experience with Sir C.V. Raman so that the audience also will be really getting motivated? Can you share your experience with Raman, Sir C.V. Raman?
Actually, I listened to a lecture, as you already pointed out, I listened to a lecture by C.V. Raman in Presidency College. That may be the year 1956 or 57. M.A. Tangaraj, who was my head of the department in Madras Christian College, where I was studying physics honors at that time, the news came that C.V. Raman is going to give a lecture in Presidency College, and M.A. Tangaraj asked all of us honor students to go and attend it. I think he also would have come. So we were sitting in the hall attending C.V. Raman's lecture. He gave a fantastic lecture, and the lecture was on his own theory of specific heat of solids. As you know, specific heat of solids, there was a big problem. The Dulong-Petit's law was not satisfied by experiment. So Einstein solved the problem. This is the beginning days of quantum mechanics by using quantum mechanics. But he used one simple, it was a first model. So he used a simple model with all the atoms in the solid vibrating at a single frequency, and he managed to explain the experimental facts. Then came Debye. Debye said that atoms in a solid don't vibrate with a single frequency. There's a continuous range of frequencies. So he used that continuous range of frequencies in his theory, Debye's theory of specific heat. Now, C.V. Raman had his own theory. He said the atoms in a crystal lattice of solid don't vibrate with all kinds of frequencies. There are unique frequencies which are experimentally known. You have to use only those in the specific heat theory. So that was his theory, and he talked about it. At one point, he became so emotional. He said Debye's theory is not worth the paper on which it is written, and he threw the bundle of papers in his hand over our heads. It flew over our heads and fell into the waste paper basket in the distance. See, such was his commitment to physics. Of course, we now later it was found that C.V. Raman, although he had a good correct point to make, and that the discrete frequencies don't make too much of a contribution to specific heat. Now we know that the truth lies somewhere in between Debye and Raman. But this story I mentioned only because to show Raman's passion for science. He had a very, very deep involvement with science. He was passionately involved in science. That's what I would like to say.
Thank you, sir. Thank you very much, sir.
Yeah.
This is Murali. I also want to you also worked with Subramanian Chandrasekhar.
I didn't work with him. I didn't work with him. I attended 2 courses by him, given by him in University of Chicago, where I did my PhD. That was in the years 1961 to 63. So he gave one course on theory of relativity, another course on mathematical general theory. I'm sorry, one course on general theory of relativity, namely gravitational theory of Einstein. The other course on mathematical physics. I will tell you one thing. In his course on general theory of relativity, when he started teaching, he said, I am giving this course because I am learning general theory of relativity, which is not a bluff, it is true, because until that time, he has not worked in general theory of relativity. Only in classical theory, all his great work was in classical theory up to that time. And he was really learning it by teaching it. The best way of teaching a subject, learning a subject, is to teach it. That's what I too believe. So that's what he did. And after that, he mastered general theory of relativity and black hole physics, and came another big tome, black holes and general theory of relativity. That is how. And also even the mathematical physics lecture, it was on generalized functions, the so-called delta functions of Dirac, and he had to master that because much of his work on black holes involved handling delta functions in very complex ways, and that is the reason why he was teaching it to us.
Yes, sir. Thank you, sir.
We have a question from chat. So, what we expect to know about neutrino oscillations from INO?
Well, what do you learn from INO? One of the aims of INO at the beginning when we planned it was to detect, to decide between these 2 orderings I mentioned when I talked about the masses of the neutrinos. Either it can be starting from below, mu1, mu2, m1, m2, and m3, or it may be m3, M3 and M1, M2 above. These 2 possibilities exist. Both are allowed by experiment because the sign of the mass square difference between 1 and 2 is still not, 2 and 3 is still not determined. And that can be determined from INO, because INO for the first time will be able to study neutrinos, get the flux of the atmospheric neutrino flux for neutrino and antineutrino separately, and that contains information about this mass square difference, the sign of the mass square difference. Basically because the neutrinos interact with the earth matter through the MSW effect, and that has not been seen. So the idea of INO is to separate the neutrino and antineutrino through the big magnet which we are making. That is the reason for the magnetic for ion being magnetized in the INO detector, and that separation of the 2 fluxes is important for getting this effect of the earth matter. Through that, the earth matter effect interferes with the other oscillation term, and hence that interference term contains the sign of the m2 squared minus m3 squared. That is the original idea. But now that it is getting delayed, I do not know whether we will be the first to determine. There are other methods to determine the sign. The Chinese, who started neutrino physics much later than us, they are already much ahead. The Diabe experiment already determined the 2-1 angle, the theta 2-1 angle, and now they are having another big experiment planned, which may come up much before. If we now start the INO experiment, there is a chance that we will be the first to determine, or we will be only the second. The second thing also is important because it's a very difficult experiment, and the confirmation of the Chinese result, if they do it first, also is important. But nevertheless, we have to start now. But these politicians are preventing us, preventing it from happening. That is the reason why urgency. But unfortunately, the election has come now, so we have to wait until that time and then start our campaign. But I want to say one thing: whether we determine this ordering of the neutrino masses or not is not completely relevant. As I said, This will be a neutrino lab which will exist for the next 50 years, if not 100 years, and many other things. Even in the neutrino sector, many other things have to be determined. For instance, the neutrino-less double beta decay, which is the most important experiment in neutrino physics now, because we are talking about neutrino oscillations, but oscillations are not sensitive to this difference, whether it's a Dirac particle or Majorana particle. Only neutrino-less double beta decay. So in my opinion, neutrino-less double beta decay experiment has to be mounted in IMO. And that is one thing. Then there are other things. Apart from neutrino physics, there is another very important area in which INO can contribute. Although it is called India-based Neutrino Observatory, it will be an observatory for detecting any elusive object like dark matter. Most of the matter in the universe is not made up of particles which we are studying, like the standard model particles. They are made up of what are called dark matter because it does not emit or absorb light. So it has been detected only through gravitational interaction so far by astronomers. But what exactly is the nature of this particle, only physicists can determine. And they are doing many underground experiments again, but so far no result. Such underground experiments to detect dark matter also will be mounted in INO cavern. Feasibility studies for that are going on in Calcutta, in the Jadguda mines, because that is a shallow lab. That will be only feasibility studies. Ultimately, that dark matter lab also will be mounted in the INO cavern. So like that, there are many other issues which INO will begin to concentrate after oscillation studies are over. Oscillation studies are not over. As I already said, the CP violating phase delta is yet to be determined.
So, if there are no more questions, shall we proceed to vote of thanks?
Excuse me, sir. Go, a student from IIITM. First of all, I want to apologize for what happened. I didn't check my phone, sir. My phone was really sensitive towards hand touch. So please accept my sincere apologies. And I have two questions, sir. First of all, sorry for asking beyond the topic of what you are teaching.
Okay, it's okay. You can ask. Yeah.
Sir, first one is scientists discovered that. Recently discovered that our Earth is rotating. Completing its day 0.05 milliseconds faster than usuals. Sir, what is your perspective behind the reason for what's happening? Maybe the Earth's moving faster, or is there any force that making Earth to move faster?
You mean the Earth's rotation speed is become faster? Is that what you are saying?
I'm asking you, sir. Maybe is the Earth is rotating faster, or some force that makes the Earth to rotate fast?
Oh, I do not know the answer to this question. I did not even know that Earth is rotating faster. If the Earth is rotating faster, our day will be less than 24 hours. But I have not noticed that. They have not announced that the day should be shortened. I have not seen any such announcement. They are still using 24 hours per day and 365 days for the whole Earth's going around the sun. So I don't know where you got this information, but if this information is correct, then see, Earth is subjected to many forces. The sun's attraction is one thing, but there are other big planets like of course, moon. Although moon is small, it is nearby, so it has its effect. So that force also is, and that already we know. The tidal forces which come twice a month are due to moon. And then there are the big planets, Jupiter, Saturn. They also do have. So in an exact calculation, all these are taken into account. But things have got stabilized for to 24 hours, 24 hours per a day and 365.25 days for the year. for a long time. Of course, these numbers are not exact, so they correct it by leap year and so on, leap year and leap century and so on. So that has been going on for some time. Apart from that, if there is any effect, I do not know. There is one effect on other even moon, I think, the so-called nutation, the exact orientation of the Earth's axis, that also changes. And then, of course, the magnetic axis of the Earth changes much faster. There is even a reversal of the magnetic poles once in many years. But that happens, I think, once in 1,000 years, something like that. I don't know. I do not know much about these subjects, but I am sure all these things are well understood. There is no unknown force which is needed to explain, as far as I know. But you should ask an astronomer, if you ask these questions to an astronomer, you will get better answers.
Okay, sir. And my second question was related to time, sir.
Yeah.
Actually, time is a relative, no, sir. Is there any chance to think that Big Bang is just happened an hours ago, but it been years for Earth?
No, I don't understand you. Big Bang is supposed to have happened 13.7 billion years ago. That is
yes, sir. According to Earth,
that is what
it's been 7 billion. Is there any chance to time is relative? No, sir. Is there any chance that being there, if being nearer to the planet, that is happen at the spot that Big Bang happened?
See, Big Bang does not happen in one spot. It happens all over the universe. I mean, there was a single dot which was the universe before the Big Bang, and that dot exploded. So that is Big Bang. And Earth or planet, nothing was there at that time.
Sir, for Earth, sir. It may be some other planet in other galaxy.
There is some interference with your speech. I don't know why. So can you ask again, because I didn't.
So it's sir. It's been 13.77 billion years that Big Bang happened for Earth. According to Earth, it's been
not for Earth, for the whole universe. For the whole universe, it happened. Earth is a very, very insignificant part of the whole universe. We are talking about the whole universe in this question.
No, sir. We are taking time now, sir. Here, 13.77 billion years.
What you are talking about time?
Yes, sir. Yes, sir.
So, what is the question about time? Of course, time is relative. Maybe you learned it from relativity, right? Time is relative in the sense that if you are if you yourself are fast moving, the time for you will be very different. So that is what relativity, special relativity teaches. But nevertheless, there is a time. Now, depending on our velocity, time is unique. Once we are in a particular frame moving with one particular velocity, of course we are moving. Earth is rotating, Earth is going around the sun, and the sun is traveling in the galaxy. Galaxy also is moving. So if you add or subtract all these velocities, add all these velocities vectorially, you can find out what is our velocity at the moment. So in this velocity, we are moving, and for us, there is a definite time. And we are talking about that time only. In all our physics questions, we are using that time. If somebody else is moving at high speed, for him or her, the time will be very different.
So for Earth only, it's been 13.77 billion years, sir.
No, practically all over the universe. Again, I go on repeating this. Practically for all the universe, the speed of, the time at which, there is, of course, the time will change depending on where you, with what speed you are going. But those speeds are all very small compared to the speed of light. So you can ignore that question. Okay? Think of one point which exploded and gave rise to all the present day universe. That is what the astrophysicists say. Of course, you can ask, how do we know? Because unlike physics or other subjects which can be tested in laboratories, it cannot be tested. That is one unfortunate part of astrophysics. Nevertheless, everything seems to hang together. They have evidence for the Big Bang. The main evidence is a so-called cosmic microwave background, CMBR, which has been detected. That was the first evidence that this Big Bang hypothesis is correct. And that is well studied now. There are many details about this microwave background radiation, which exists everywhere. It is a microwave radio wave, which is there everywhere, which was detected, I think, in the 70s. Now it has been well studied. Many satellite observations, as well as ground-based observations, have amassed an enormous amount of data. All our present knowledge is based on the study of that. So there is no doubt that the Big Bang occurred, although we cannot prove it in the laboratory. Because the Big Bang left its signals, and those signals are one of the signals is the expand. First of all, the expanding universe. Hubble discovered the redshift of all the galaxies going away from us, and that's what gave rise to the idea of the expanding universe. If everything is expanding at one point, if you reverse the time, everything will come to a point, and that is the Big Bang. So there are ample evidences. Hubble's discovery, and then the discovery of the cosmic microwave background, and so many other things. And then the whole story hangs together. So there is no doubt that this is correct.
Yes, sir. Understood.
Yeah. Thank you.
Thank you, sir. Sorry if I bother you, sir.
No, not at all. No botheration. You have to raise questions. That is the only way to for science, for you to advance in understanding science. Science itself advances only by asking questions. I mean, Einstein proved Newton wrong. That is how he created relativity. Remember that. So you have to always ask questions, doubt what the scientists say, doubt what the books say. I think it is a right point of view. Please continue with that critical attitude. Examine whatever the scientists say with a critical mind. I think that is the sure sign of science, progress in science. All of science did not come from heaven. It was created by scientists by asking questions only.
Okay, sir. Thank you, sir.
So now if no one has any more questions, we shall proceed to vote of thanks by Vinil. So over to you, Vinil.
Yeah, thank you, Himanshu. On behalf of our institute, ITDM Kurnool, I extend my sincere gratitude for spending your precious time with us and for giving us valuable information. Especially the topic was really interesting, and we would definitely try to explore more from your input, sir. Once again, I thank all the participants, Director Sir, Professor Satyanarayana Sir, Joseph Sir, Preeti Meher Ma'am, and all other student participants. Thank you for being with us today. Thank you, sir.
Thank you.
Thank you, sir. Thank you very much, sir.
Thank you.
So we'll close the session, sir.